Good morning, aspirant. Hope you all are doing well, your days are going productive, and you are doing excellent in your work. So, here we will thoroughly look into proton magnetic resonance spectra, and we are going to cover in pretty much details. We are compiling it from all standard books, right? Before getting into this lecture, I hope you have watched the introduction of this lecture, basic of NMR spectra. Now, one each one NMR spectra. I will be sharing this whole PDF and you can download it and you can have this printout, but I will recommend that you make your own notes. Watch this, take it as reference, but make your own handwritten notes because that will be picturized in your memory. You will understand the things best with your handwriting only. So make your own notes. Okay, so now proton magnetic resonance spectroscopy. So our spectroscopy name was nuclear magnetic resonance spectroscopy. If the nucleus is of hydrogen, that is called proton. So this is proton magnetic resonance spectroscopy when we will be talking about proton nucleus 1H1. Only one proton present is nucleus. So PMR, proton magnetic resonance. Only one proton present in nucleus. In 1H1, in nucleus there is no neutron. Only one proton. That's why it is called proton magnetic resonance. Otherwise, we will be calling it hydrogen magnetic resonance. We can call it proton because nucleus only contain proton. Now, number of spin state. In last class, I have told you about spin multiplicity. I value is half for hydrogen. So spin multiplicity will be 2. That means it will be splitted into two state, alpha and beta state. Now in isolated state, what does this means? In isolated state means there is no magnetic field. There is no magnetic field surrounded by this proton. Suppose I have one proton. So this proton, my proton, either will be having spin in clockwise direction or having spin in anti-clockwise direction. If rotating around this direction generates magnetic field like this, that upper portion south, lower portion north, then opposite rotation will give the opposite type of magnet. So both nucleus have same energy. This one and this one will have same energy. That means suppose I have two nucleus, I have two hydrogens. If one has spin like this, so it is south north, otherwise other one will be north south. Sorry. Okay. Now. So south north, north south, this will have same energy. That means this will be degenerate state, degenerate nuclei. Without magnetic field, nucleus energy is degenerate. That means same energy. So external magnetic field is required. Otherwise, in any spectroscopy, we need a transition. Transition possible only if there is two different energy state. But when there is no external magnetic field, then these two nuclei has in the same level. So no transition is possible, right? What happens in external magnetic field? Why we are applying magnetic field? Because a magnet interacts with another magnet. If we want to distinguish between these two, only another magnet can do so. Now, suppose this nucleus I have taken like in this way, and this nucleus I have taken in this way, and overall I am putting an heavy external magnet where this is north pole, this is south pole. Now look at very carefully. This is north pole. That means this north pole will be repelled. We know north repulsion, north south attraction. This section south is repulsion, right? For this nucleus, north south attraction, this is attraction. So this nucleus is enjoying attraction from both sides, but this nucleus is having a repulsion from both sides. Now you can tell me which one is more stable. This one is more stable, this one is less stable. That means energy of this nucleus will be lower because it is more stable, and energy will be higher Now, the nuclei which was initially in degenerate state, it will be splitted because one has now high energy, another one is low energy, right? So, this is without magnetic field and this is with magnetic field. With magnetic field, what happens? Now understand the graph. This is energy. This is B naught means external magnetic field. External magnetic field is B naught. So when we are at this point, B naught is 0. That means this is degenerate. Now when we are increasing B naught, it is splitted. More B naught, more the energy gap. Right? Now, so some nucleus will be in ground state. Some nucleus will be in excited state. That means energy low, energy higher. Lower state is called alpha state. Higher energy is called beta state. Now, what will happen if I apply radio wave, then transition from alpha state to beta state will occur. Okay. Without B naught, that means without external magnetic field, degeneracy will be 2I plus 1. Degeneracy, here degeneracy is 2, that means two states are in same level. So this is basically nothing but 2I plus 1, 2I plus 1 like this. Okay. With B0, degeneracy is 1 because this is now splitted. So this state has degeneracy 1, this state has degeneracy 1. Now, from this graph, we know that more the B naught, more the external magnetic field, more this separation will occur, more this magnetic field, more it will repel or more it will attract. That means energy will be very lower, energy will be very higher. So separation will be, energy gap will be much more, isn't it? So B naught proportional to delta E or delta E proportional to B naught. If we remove this proportionality, replace this proportionality with equal to, it comes gamma B naught. One constant we introduce, constant is gamma B naught. Gamma B naught is now our constant. Delta E equal to gamma B naught H cross. Now what is gamma? Gamma is called gyromagnetic ratio or gyromagnetic ratio. So here we have introduced a constant that is gamma H cross. H cross means H by 2 pi. In quantum, we use H cross pretty much. Okay, so this is clear. Transition alpha to beta will occur if delta E matches with the energy of radio wave. This is a very fundamental concept because suppose I have these two energy levels and I am giving one energy. Only this transition will occur if energy of this matches with this energy gap. Now, we know delta E equal to gamma B naught H cross. We know delta E equal to H nu absorbed. Forget it. Delta E equal to gamma B naught H cross. So delta E means H nu cross because for transition, what will happen? The frequency of radio wave, that is H nu absorb, it is basically equal to delta E. So delta E equal to H nu absorb equal to gamma B naught H cross means H by 2 pi. Now H cancelled out, gamma nu absorbed equal to gamma B naught by 2 pi. So these expressions are very much important. Why? Because in exam, numerical question comes from this systems, this type of equations. Now, interaction of radio wave with the ground state of nucleus. Now, this radio wave interact with ground state, and with that interaction, if the energy if matches with this energy gap, then it excites. Now, how this interaction occurs? Let's see. Principle of precision and resonance. There is something called precision and resonance. We will understand that. Suppose in isolated state means there is no external magnetic field. Suppose a nucleus is rotating like this. This is rotating axis. And beta n is basically the magnetic field generated by this spin. We know moving charge always generate magnetic field. So this is basically magnetic field generated by this system. And this is very small, isn't it? Now, what happened? I have applied external magnetic field B naught. What will happen? This axis will rotate. This axis itself will rotate to another imaginary axis. This is called British. This is called precision. The spinning is still continuing, but this axis is now rotating to another imaginary axis, or this axis is making one circle in the space. Rotation about own axis generate magnetic field, but precession generate electric field. Now this is a very fundamental thing and very deep thing actually. Why? Because if my system is going to interact with electromagnetic radiation, then property of my system have to be matching with this property of electromagnetic radiation. We know in electromagnetic radiation there is something electric field, something magnetic field. So in my system, if these two components are missing, then this system will never interact. Here rotation about own axis generate magnetic field, but this precision will generate electric field. That means it is kind of electromagnetic system is generated. Okay. So in precision, both electric and magnetic field is present. So precisional frequency has both electric and magnetic component. Now it can interact with radio wave. Many students don't know it. They read just about reading, but they don't know why I need external magnetic field. Why the precision is required actually. I think it's now clear to you. Okay. Beta n equal to generated magnetic field by the rotation of proton along its axis itself. We know this. Alpha state, beta state, and nu absorbed. Okay. So precisional frequency must be equal to radio frequency for transition by resonance. For resonance or for transition, precisional frequency should be equal to absorbed radio frequency. This is the condition of resonance. And this is a very popular question, by the way. What is the condition of resonance? Okay. Now, this formulas again I have written here. Delta E equal to gamma H cross B naught. New precisional frequency equal to gamma B naught. So these both are mutually new precisional frequency. So from here, this formula is coming new precisional frequency equal to 2 pi nu absorbed. Okay. This gamma is called gyromagnetic ratio. This is internal property. That means it depends about the nucleus. It is internal property of individual nucleus. Indicates the splitting tendency of a nucleus in same magnetic field. I am applying same magnetic field. So gamma indicates how much it has tendency to split. Suppose I have 1H1. This has this amount of delta G. I have applied same external magnetic field B naught. But proton nucleus has splitted this much. But carbon nucleus has splitted this much. Delta E1 is larger than delta E2. Why? Because gamma of 1H1 is more than carbon nucleus. It is actually 4 times. Actually, it is 4 times. So it basically tells you what is the tendency of splitting. I am applying same amount of magnetic field, but different nuclei will tend to split in different extent. And this is basically uh, emphasized by this gyromagnetic ratio. In some numerical, these things are also sometimes given. Delta E proportional to B naught, delta E equal to, H nu absorbed equal to Gn mu n B naught. Gn is nuclear G factor, mu n is nuclear magnetic moment. Nu absorbed equal to Gn mu n B naught by H. So sometimes in numericals, these things basically coming from theories of physics. We don't have to understand this pretty much, but I have written this formula. If anywhere it is required, if you remember it, it will be beneficial for you. Okay. Now, one more thing. just remember 60 megahertz equal to 1.4 Tesla for 1 H1 NMR. Sometimes you have to do unit conversions from megahertz to Tesla. So 1.4 Tesla equal to 60 megahertz. Okay. Now, concept of extra nuclear part. Now we have understood what happens in nucleus. If we summarize it, what happens in nucleus? Initially, when there is no magnetic field, then nucleus was in degenerate state. When I have applied external magnetic field, this is splitted into two state, alpha and beta. If I applied more external magnetic field, then this separation is more, then more separation. This is basically a line like this. This is E and B naught, right? And some formulas we have seen. And when we are applying magnetic field, then what happens? Two things happen. Basically, splitting is occurring, and second one is precision is occurring, right? Now, concept of extra nuclear part. Now, it is a apparently it seems that it is a phenomenon of nucleus only. There is no role of extra nuclear part. Extra nuclear part means electrons, because it is everything is occurring inside the nucleus. Has there any role of extra nuclear part? That means external electrons. Let's see. Nucleus, in nucleus it is having spin and it is generating magnetic field beta n. Now, in surrounding there are electrons, and electrons are also charged particle, so they are also moving, and they are also moving means they are also generating magnetic field. Suppose this is beta e, that means magnetic field generated by electron. More the electron cloud, more will be the beta e. More will be the electron cloud, more will be the beta e. That means this beta e will hinder, will shield this beta n. Now see, I am applying this external magnetic field. Now, what I am supposed to do, this external magnetic field will have to interact with this nucleus, and eventually this nucleus will split and transition will occur. But if in surrounding there are so many electron clouds, then eventually this external magnetic field will not reach to this nucleus in a good manner. So this electron density is basically hindering the external magnetic field. So effectively, beta naught, I am providing beta naught, but some part is being encountered by these electrons. So eventually for this nucleus, effectively beta naught minus beta e, this amount of magnetic field is getting reached in the nucleus. So beta effective means beta naught, that means the magnetic field I am applying, minus beta e, magnetic field reduced by these electrons. So that means external electron also plays a crucial role, right? So we know new precisional frequency proportional to beta effective. So more the precision, more will be beta effective. Now, okay, one more thing. More number of electron, that means more number of electron means it will shield this nucleus. So we will be calling it shielding, and other one we will be calling it de-shielding. Okay. Now, suppose I have two systems, carbon, hydrogen, and fluorine. With carbon, hydrogen, fluorine, and with carbon, hydrogen, and chlorine. Now, let's see. The question is new precisional frequency order. Now, this is HA, this is HB. We know this is, we are reading proton magnetic resonance, so we will be observing proton only. For first case, we know fluorine is very much electronegative, so it will drag electron, and eventually carbon will drag electron from HA. So this HA is de-shielded and this HB is shielded. It is de-shielded means, it is de-shielded, that means electron density is less. That means if I apply magnetic field, then more magnetic field will reach to the nucleus of HA. More magnetic field will reach to nucleus of HA. That means this nucleus will have precision with more precisional frequency. More it will have more precision, it will have more precisional frequency. So it will have more positional frequency than B. HA is more deshielded. HB is more shielded. Deshielded means not shielding. If more nucleus, if more electron, that means more shielding. Here electron is dragged up by fluorine, so it is deshielded. So deshielded means new value will be higher. A will have more external magnetic field, right? HA will have more external magnetic field. Okay. Now there is something called Boltzmann distribution, and this is basically gyromagnetic ratio value. For hydrogen, it is 42.57 megahertz per Tesla. For carbon, it is 10.705 megahertz per Tesla. As I have told you, it is basically hydrogen has 4 times gyromagnetic ratio than the carbon. It is the actual value. Now, there is something, this theory was given in a book. This basically how many nucleus will be in ground state or how many nucleus will be in excited state will be depending on Boltzmann distribution. If you have understood Boltzmann distribution, then only you will be able to understand it. I am not going into deeper because it is not so much important. Sensitivity. This is basically sensitivity. Okay, sensitivity of NMR. Hydrogen NMR is more sensitive than carbon NMR. Carbon NMR is less sensitive. That means more amount of sample is needed. Less sensitive. That means we have to put more sample to have a good result. And less sensitive means need more time to take the spectra. So carbon NMR takes more time and eventually more number of sample, more amount of sample is needed to analyze carbon spectra. Okay. Sensitivity depends on two factors. First one is abundance. Sensitivity proportional to abundance. Abundance means in nature how many how many percentage of this nucleus is present. Abundance, natural abundance. Second one is gyromagnetic ratio, sensitivity proportional to gyromagnetic ratio. Eventually hydrogen has more gyromagnetic ratio, that's why eventually it has more sensitivity. Now graph of PMR, proton magnetic resonance, how the graphs look like. In a graph there is two important things. In a graph, in any graph, first one, suppose it is one graph, this is one graph. First one is position of peak, these are positions. Second one is intensity of this peak, this is intensity, this is higher intensity, this is higher intensity, this is lower intensity. So in a graph basically two components are there, position of a peak and intensity of a peak. So let's first read position of a peak. It is described by term called chemical shift delta. There is something called chemical shift called delta. What is this chemical shift? Chemical shift delta, it is expressed in unit ppm. Unit of delta is ppm. The formula is new precisional frequency. We are studying proton NMR, so precisional frequency of proton minus precisional frequency of reference compound. That means in any compound, my sample is dissolved. After that, it is taken for NMR analysis. So this this compound or solvent, it is called reference compound. So formula is new precisional frequency minus new precisional frequency of reference by operating frequency. That means machine frequency of NMR machine. Now first two data, first one it is in hertz, this is in hertz, this is in hertz, and machine it is in megahertz. So eventually hertz by megahertz, that means 10 to the power minus 6. So this unit is in ppm unit. Okay. There is something called shift. This part, numerator, it is called shift. And overall, if we divide it with operating frequency, it will be chemical shift. Unit of shift is hertz because hertz minus hertz, so hertz. And I am dividing it with megahertz. So it will be ppm. Chemical shift will be having unit ppm. These things confuse us very much because in exam, suppose I have these data are given in megahertz, but you have to put it in hertz, and answer of shift will be always in hertz. Now, reference compound. Which reference compound is used in NMR? That is called TMS, tetramethylsilane. This is compound tetramethylsilane, silicon 4-methyl. Eventually, all these hydrogens, all these 12 hydrogen are similar. And among carbon and silicon, carbon is more electronegative. That's why these hydrogens are shielded. This is highly shielded. Highly shielded means beta effective will be lower. Beta effective will be lower means positional frequency will be lower. Positional frequency will be lower means this will be lower means delta will be lower. So delta for TMS is very, very lower. That's why it is taken as 0. That's why as it is taken as 0, we call it reference compound. Now, why it is chosen as reference compound? These are the reasons or features of reference compound. Question can come like this way: what are the features to have a reference compound for NMR? This will be answer. Or the question can be framed like that: why TMS is used as reference compound in NMR? First one, reference compound should be chemically inert. It should not react with my sample. Suppose my sample is A and this is TMS. If I put it, if they react, then my compound will be decomposed. I will not able to analyze that. So chemically inert. Next, reference compound should have magnetically isotropic proton. That means one type of proton. Here all protons are similar. So 12 similar protons. All protons should be similar. If protons are not similar, if only one type of proton, then only one signal. If more type of proton is there, if there was 12 different type of proton, then we will having 12 different signals. So there is no use. Which point I will take as reference? Right? There will be confusion. So it is used basically because here all protons are equivalent, all are isotropic. Now, reference compound protons should be most shielded compound compared to organic sample. Now, most shielded, we can see these protons are shielded. Shielded means delta very, very low. So, other organic compounds will have delta more than it. That's why reference compound should have most shielded proton compared to common organic sample. Fourth, reference compound should be volatile so that it can be easily removed. Suppose my compound, this is TMS, and I am using my compound. I have analyzed with NMR. Now I want my sample back. Suppose my sample is very precious. I want this sample back. So if TMS, if it is difficult to remove TMS, then it's problematic. So it should be volatile so that if we heat it, then TMS will be vaporized. I will be getting back my compound. Now, mostly organic compound sample should be dissolved in this. Everything, almost every compound dissolves in it. Peak of reference should be intense enough. Now, intensity of peak depends on how many number of protons are there. Here, 12 protons are there. 12 protons are there means intensity will be very higher. So, easy to analyze. So, with this, other compounds will have lesser intensity, right? That's why it is used. Okay. There is some questions. Leave it. I don't know what is written here. Okay. Now, factors affecting chemical shift. What are the factors that affect this chemical shift? First, type of proton, steric effect. Steric effect, or it is called field effect. When a proton is 1 degree, 1 degree means this proton connected to this carbon, this proton is connected to this carbon, and this carbon is connected to only one carbon. That's why it is 1 degree. If this carbon is connected to 2 proton, this is 2 degree. If this carbon is connected to 3 carbon, that is 3 degree. In 3 degree, there is more steric hindrance, more electric field. That's why here more steric effect, and more the steric effect, more will be delta value. That's why for 1 degree proton, delta is 0.9 ppm. For 2 degree, 1.3 ppm. and for this 1.7 ppm. You can memorize it in a very good way. First one 0.9, second one is plus 0.4, third one is also plus 0.4. In this way you can memorize it. With increasing steric hindrance, electron density of hydrogen shift at one direction, making it more deshielded, right? It is more electron density, so it will repel this electron, so electron density will be shrinked into this. So now more portion is vacant. So if we put more external magnetic field, if we put magnetic field, so it will reach more to the nucleus. More, it will reach more to the nucleus means nucleus will have precision more frequently, so precisional frequency will be higher. More the precisional frequency, more the delta. Easy. Now, very important, very important, anisotropic effect, pi field effect, or secondary field effect. First one, it is called field effect. It is called secondary field effect. Very much important. Be very attentive. Anisotropic effect. Magnetic field lines are directed towards perpendicular direction to the path of movement of electron cloud. Okay, I am turning off this class. In this next session, I will be discussing this with you. Okay. If you have any problem in this section, uh, up to this point, you can comment below, and you can comment if any other queries you have. In the next class, we will be starting from there. Thank you.